So coming back, so Edward is an old friend. He's a professor at Berkeley. He is a graduate from Berkeley, from Professor Dave Messerschmidt. Then after a short period of AT&T Bell Labs, he decided to come back to Berkeley, and he has been with the faculty since then. He's recently retired, so to speak, meaning that he doesn't teach anymore. We are so happy that convince him to come in and teach this class. So Edward has been famous for his work in system level design, in particular in his contribution to Ptolemy, who is a tool that has been, in our portfolio for many years and has been used all over the world, and is open domain. So if you want to use it, you could use it anytime and any place. Today, Edward is going to talk to us about his latest work that is related to our last class when we were talking about the wrapper and the model computation of Matter 2. And in particular, we talk about Lingua Franca, and actually Edward's latest work is about Lingua Franca. Edward?
Okay, so I'd like to talk about a current project in my group right now, where we're building a model of computation that we call Reactors, that is based on discrete event systems, and an implementation of that we call Lingua Franca. And I think it connects rather strongly to several of the themes in this course, and also to a lot of the work that Alberto has talked about, like the Metropolis work. And I'm not exactly sure what the connection is with the Lingua Franca that Alberto has talked about, but maybe he'll be able to clarify that as we go. So the focus of this project is on cyberphysical systems, which I don't have to say much about here. I think you all know what these are about, so I'll just skip over that. But I want to go directly to a challenge problem that I think motivates a lot of this work. It's a very deceptively simple challenge problem from a cyberphysical systems scenario. And it's meant to be representative of a whole class of problems that arise in factory automation systems, in vehicle automation systems, and so forth. So the goal in this challenge problem is to automate an aircraft door. And you would think that an aircraft door would be a relatively simple thing, but it's not actually quite so simple, because the door includes a automatic deployment of escape slides. And if you open the door while it's armed, you get a rather disastrous, potentially disastrous situation where the slides could accidentally deploy, and it's really a safety critical issue if you actually allow the slides to deploy at the wrong time. So you need to disarm the door if there is a ramp that is adjacent to the aircraft before you open the door. And the way that this is currently done is very much manually. So a flight attendant looks out the window and is not permitted to disarm the door until the flight attendant has verified visually that there is a ramp outside the door. And then the flight attendant disarms the door, and a red flag changes color to a green flag through a little window that a person outside the aircraft can see. And the person outside the aircraft then can safely open the door without getting the slides deployed in their face. Okay, so the challenge problem is that we're going to put a microprocessor into the aircraft door, and it's going to provide a service that can automate the opening of the door. So it doesn't have to be done by a person standing there. It could be done from the cockpit, for example. So simple challenge problem. I don't know if it's probably not a realistic challenge problem. I seriously doubt that this is very high on Boeing's to-do list to automate aircraft doors, but I think it illustrates quite a number of features. So the idea is that we're going to have this microprocessor, we're going to connect it up to the network, and it's going to provide two services. So we'll simplify the problem. We're not even going to worry about how you close or arm the door. We're only going to worry about disarming and opening the door. So assume that the state of the door is closed and armed. The challenge problem is really deceptively simple. What should your software do when it receives a message to open the door? Seems like an astonishingly simple problem, but it isn't really that simple. Let's look at what an architecture might look like that uses this service. So you've got the door controller sitting on the network, and it can receive disarm messages and it can receive open messages. And maybe to replace the flight attendant that looks out the window, there's a picture that I took. It seems like a distant memory when one could actually get onto airplanes, but it is not that long ago that I took this picture. In fact, it was in December. And there's a flight attendant looking out the window before disarming the door. And you could replace that functionality with an embedded vision system that issues a disarm message whenever it identifies that there is a ramp adjacent to the door. Then, of course, you might have a cockpit control that sends disarm and open, and maybe you have a fire detection system in the airplane that will issue an open message, and it wants the door to be opened whether it's armed or not. So presumably it would be disarmed if the fire occurs while the door is at the gate, but it will be armed if the fire occurs while the aircraft is away from the gate. So let's suppose that the network uses any of your favorite communication fabrics. So maybe it uses publish and subscribe, like you might find in ROS, for example, the robot operating system, or in MQTT, which is a very popular publish and subscribe bus used in Internet of Things applications, or Microsoft's Azure or Google Cloud, which are used in enterprise computing pretty heavily. These are all publish and subscribe buses. Or maybe you're particularly fond of message passing schemes like Actors, as implemented, for example, in Akka or in Erlang. Erlang has been fairly widely used in embedded systems, and it uses a message passing architecture. Or Ray, which is an actor-oriented framework from Berkeley. Or maybe you're particularly fond of service-oriented architectures, which are essentially remote procedure calls. And you like gRPC, for example, which is an open source remote procedure call framework from Google, or Apache Thrift, or something like that. So these are service-oriented architectures, are basically remote procedure calls. Or maybe you like shared memory systems, distributed shared memory systems, like ones that are based on Linda, for example. Those are not quite as fashionable as the other three classes of systems today, but you still find occasional uses of them. So suppose you're using any one of these. For example, you're using Actors, so there's messages flowing. The question remains, what should the software do when it receives a message to open? And the challenge here is that none of these communication fabrics have any semantics associated with the order of messages. And so it's quite possible that a disarm message was launched into the network before an open message was launched into the network, but your software received these messages in the opposite order. And in that case, you face a rather difficult problem, right? Because when you receive the open door message, you really can't be sure that there hasn't been sent a disarm message. So what are your possible solutions? Well, you could just open the door. So that's probably, naively what your first implementation of the software will do. And there's a pretty good chance that when you test the system, it'll actually work just fine. You'll never get an accidental deployment in the testing because maybe your network behaves pretty well and messages get delivered in the right order, and you never get quite the coincidence where a disarm message ends up being very closely spaced in time. But how much should you test, and how much formal verification should you do on the system, and how do you constrain the design of the other components, and how do you constrain the design of the network to ensure that the system is safe? Those questions all remain pretty wide open. So another approach that you might take, which is a much more sophisticated one, would be to develop a distributed consensus. So you, for example, send a message saying, you broadcast a message on the network saying, well, the door is armed, so I'm not really sure that it's safe to open it. So maybe you would like to ask all the components that have an interest in the door and wait for responses. But how many responses are enough, and how long should you wait? And what if a component has failed and never responds? If your fire detection system is one of the critical parts of the aircraft and it has to open the door in an emergency, there's a very good possibility that other components have failed. So probably you're going to have to go and read all of Leslie Lamport's papers on how to develop a distributed consensus, particularly in a fault-tolerant context. And many of these papers are actually about impossibility results, about things that you really can't do with a distributed consensus. So this is going to turn what seemed like a very simple embedded software engineering problem into a rather big project that's a whole lot more difficult to carry out. So here's another possible solution, and this one is sort of an intuitively appealing solution, and maybe one that you would stumble upon, which is just wait a little while and then open the door. So the theory behind this solution is that if a disarm message has been launched into the network, and things are working reasonably well, you should expect to see it before too long. And so you make an estimation of maybe how long that might take, and you wait that amount of time before you open the door. But then the question becomes, well, how long should you wait? And if this is a safety critical system and you have to be able to defend your decision to a board, for example, like the FAA, that it has to certify your software, how do you defend the decision about your choice to wait 10 milliseconds or whatever you choose to wait, right? So you could come up with something very ad hoc, but how can you be sure that it's right? So in some ways, none of these solutions is very satisfactory. Now, you could say, well, all right, I believe in formal verification, so let's try to fix this with formal verification. We'll design some system and then formally verify it. In order to formally verify a system, we need some formally stated requirements. So let's try to come up with some requirements. So here's a couple of properties that you might want to satisfy. The first one is that if a door receives open, it will eventually open the door, even if all other components fail. Okay, that seems like a reasonable requirement. A second requirement might be if any component sends disarm before any other component sends open, then the door will be disarmed before it is open. So the question is, this again seems like an intuitive sort of requirement, but the question remains, can these be satisfied? And can I in fact verify that they will be satisfied? The first one is the one that makes a distributed consensus solution challenging, right? Which is that it's hard to develop a distributed consensus in the context where components can fail. The second one is even more problematic because it uses this word before, and it's using this word before in a statement about a distributed system. And in a distributed system, you don't actually have a common notion of time. In fact, we know this fundamentally from physics, okay? The order in which two events occur, according to the theory of relativity, is dependent on the observer. And so there isn't actually in physics a very clean notion of before. Now you could say, all right, you're just nitpicking here. We're not talking about relativistic effects here. I mean, planes don't go that fast, right? So you're not going to get close to the speed of light. You're not going to have to worry about relativistic effects. And certainly that's fair enough. But relativity aside, the fact is that any distributed system does not actually have a common time base to reference. So if we want to nail down this requirement in some formal way, we're actually going to have to establish a model of time that is something that we can defend independently for this distributed system. So these two requirements are actually problematic even before we try to figure out how to verify whether these requirements are satisfied by some implementation. And my conjecture is, in fact, that these two requirements cannot be satisfied for a sufficiently complex system unless you make some additional assumptions about the system. So you have to make assumptions on, for example, bounds on network latency or bounds on clock synchronization. So formal verification doesn't seem like a silver bullet. These are the four classes of network fabrics that I suggested that we might want to use: publish and subscribe, actors, service-oriented architectures, or shared memory. And in fact, these are extremely widely used. These are very common in this kind of scenario. So let me pick particularly on actors. Why is it that actors don't actually give us a way to solve this problem? So let me explain what actors are. So actors, as first introduced by Carl Hewitt in the 1970s and then developed by Gul Aga in the 1980s, are essentially bundles of data plus message handlers. So you have some actor X, it has some private data, and it has a message queue, and messages come in over the network, and messages are labeled in such a way that they can be dispatched to handlers. So if a message is labeled to invoke handler A, then when it gets to the head of the message queue, handler A will be invoked, and handler A could then go and issue further messages. So let's try to write some code. Let's implement this aircraft door example using actors. And this is using a syntax that's very similar to Ray and also similar to Akka, which are two very popular actor frameworks. So in this case, the source of messages, in this case, in both Ray and Akka, typically the source would have a handler main, or somewhere in the system there would be a handler main, which is the first handler that gets invoked, and that creates other actors. So here it creates a new door, which can be instantiated on a remote machine. And then it sends it a message to disarm. It's very common in actor frameworks to make this sending of a message look like a remote procedure call, but it's not actually a remote procedure call. It's syntactically represented as if it were a procedure call, but it's not a remote procedure call. It's a send and forget kind of semantics. So this will send a message to the instance X of door to disarm. And then it will subsequently send an open door message, okay? So the door actor has, in this case, two handlers, one that will respond to an open door message and one that will respond to a disarm message. So the first question is, what are the assumptions that are needed for it to be safe for the handler to open the door? Okay, that's the question. And that question is actually relatively easy to answer for this simple system. If we can use a network fabric that has, first of all, reliable delivery of messages and in-order delivery of messages, so it will guarantee, the network fabric will guarantee that the recipient will receive the disarm message before the open door message, then this design is probably safe enough. And fortunately, network fabrics that provide those kinds of guarantees are relatively readily available. You could use TCP/IP, for example, the most commonly used protocol on the internet, which does, in fact, provide reliable in-order delivery of messages. So if you have a TCP/IP socket connecting these two actors, you will be, in fact, guaranteed that, barring a hardware failure somewhere, that the open door message will be handled before the disarm message, or vice versa. If the disarm message is sent first, then the disarm message will be handled before the open door message is handled. Okay, so that's what we want. But now let's change the design ever so slightly by routing the disarm message through an actor. This might be an actor that implements, for example, the embedded vision system. So this actor will decide whether or not it's actually safe to disarm the door by determining whether there's a ramp adjacent to the door. So now the architecture looks pretty similar, except that the main actor creates two other actors, a door and the gateway actor, the pass disarm. And then it sends a message to the pass disarm, which will then forward the message to disarm. And then it sends a message to open the door. And my question is, now what assumptions are needed for it to be safe for the handler to open the door? In this architecture, TCP/IP will not solve the problem. Okay, the socket connection can only connect pairwise, and having in-order reliable delivery on any of the pipes between actors is not going to be sufficient to guarantee that the disarm message will be handled before the open message. So TCP/IP will no longer be a suitable networking fabric to build this on. And in fact, you're going to be pretty hard pressed to find a suitable network fabric. You're probably going to have to go down to a rather very low level design here, where you use a specialized network like an ARINC bus, you use time-slotted communication, and you're going to have to integrate the network design into your application design really quite tightly. So are there better alternatives? Well, there are. There's many possible ways of dealing with this. One is, of course, you could ignore the problem. That's probably the most common solution to such things. You could design your system including a very careful design of the network, and then come up with very detailed models of how the network behaves, how the processors behave, model all the timing, execution time of the software in each of the components, et cetera, and use that model to verify that messages will be handled in the correct order. Or you could rather more simply just change the model of computation. So there's a number of possible candidates here, and you've probably seen several of these in this class, and any one of these can be used actually to solve this problem. But I'd like to focus on the one that we use in this Lingua Franca project and the Reactors project, which is a discrete event model of computation. So what is the discrete event solution for this problem? Well, the solution is to give a semantics to the ordering of messages, and we do that with timestamps. So we introduce a notion of a logical notion of time, and the embedded vision system, if it issues a timestamped message with timestamp T1, and the fire detection system issues a message to open the door with timestamp T2, then the order in which these will be handled will be dependent on the numerical order of these two timestamps and not on which message arrives first. Okay? So the implementation of this system, the goal of the implementation is to guarantee that messages are handled in timestamp order. And then once you've got a guarantee that messages are handled in timestamp order, you can design this system and provide formal requirements and provide verification that your design meets those requirements on the assumption that the underlying implementation does in fact handle messages in timestamp order. Okay, so this use of timestamps is very old. It dates back at least to the 1950s, when it was starting to be used to build fairly large-scale simulation systems. And there's a long history of work with discrete event execution engines, including hardware description languages, which are pretty much all discrete event languages. They use timestamped messages. And network simulation tools are also using timestamped messages. And many large-scale simulation systems use timestamp messages. And there's a long history of work on how to actually execute discrete event systems in a distributed way. So in particular, the challenge there is ensuring that messages are handled in timestamp order, even though you're actually executing on different microprocessors scattered across a network. Now, the thing that we're doing different compared to most of this history is that we're using this language not as a simulation language, but rather as an implementation language. So it's in some ways, this work is much closer to the hardware description languages than it is to the software uses of discrete event, because the software uses of discrete event have historically been pretty much mostly simulation. But there are some exceptions. So one of my favorite exceptions where the discrete event model is used in a very large scale software deployment system is Google's Spanner. Now, the aircraft door example that I took as a challenge problem here is a very, very small example. Google Spanner demonstrates that the concept that I'm going to talk about is not limited to small examples. In fact, it scales to extremely large systems, even systems that span the globe, that run in multiple data centers, that run in hundreds of thousands of processors simultaneously. So what is Google Spanner? Well, Google Spanner is the underlying database fabric used in distributed database systems by Google. So Spanner is designed as a replicated database where the data of the database is replicated in data centers around the world. So this map shows at one point in time Google's data centers scattered across the US, and the database might be used, for example, for an airline reservation system. So you might have a query that comes into the data center in Seattle that wants to reserve an airline seat. So it updates a record to mark that airline seat occupied. And around the same time, you get a query that comes into the data center in Dallas that is asking, is this airline seat available? And you'd like to know, how should Dallas respond? Okay. So what Google Spanner does is it timestamps these two queries. So the query that is trying to reserve the airline seat will be timestamped with timestamp T. The query that is asking whether the airline seat is available will be timestamped R. And then the semantically correct answer that Dallas has to give depends simply on the numerical order of those two timestamps. If T is less than R, then the right answer from Dallas is that the airline seat is available. If T is less than R, then the right answer from Dallas is that the seat is not available. It was reserved at an earlier logical time. If, on the other hand, the T is less than R, is greater than R, then the right answer is that the seat is available. Okay, so now we have a definition of what the correct response is from the database, and our goal is to build this distributed system in such a way that it realizes that semantics. So here's a cartoon of what this would look like if you built this as a Lingua Franca program. You would have on one computer somewhere a reactor that is implementing a web server. So it's simply accepting queries that are coming in as HTTP requests. You have your reactor that is a database that will handle these queries by updating the local copy of the database, and also by then broadcasting an updated record to all other copies of the database. So on another computer somewhere else in the world, you have another chunk of code that consists of a reactor that has a network interface that handles these incoming messages to record updates into its copy of the database. And you also have a web server here that is responding to queries. Okay, so the scenario that I just described is where suppose platform A is in Seattle and a query comes in that is trying to reserve the airline seat. That will get timestamped with timestamp T. And in Dallas, the web server gets a query, is this seat available? And that gets timestamped with timestamp R. And the correct answer depends now on the numerical order of these two timestamps. But of course, these two timestamps are on two different machines, separated by a rather substantial distance. And so you can't just directly compare these two timestamps. So the question is, how should Dallas reply to this query R? So one thing, of course, that it could do is simply wait for messages from Seattle, and then it has timestamps that it can compare. But that's obviously not going to be a very good solution, because it may have to wait a long time for messages, because there might not be anything happening with this airline seat in Seattle. So how can you solve this problem? Well, there's a number of classical ways of solving this problem. One of the oldest ones is called the Chandy and Misra approach. And this approach makes the assumption that events arrive reliably and they arrive in timestamp order. And all it does is it simply does what I just described. It waits for messages from all possible sources and then compares those messages. And once it determines that a message with timestamp R1 is less than T1, then it can safely process and issue a reply. Because of this assumption that events will arrive reliably in timestamp order, it's assured that it will not later see an event with an earlier timestamp. But this is problematic. And the Chandy and Misra way of dealing with the problem is that you don't want to have to wait forever for a remote component to send you messages. So every component has to generate null messages, and it has to generate those fairly frequently. So these are null messages that basically say, I have nothing to say, I have nothing to say, I have nothing to say. And it timestamps each of those messages, okay? And it creates quite a bit of network traffic. A second problem, which is particularly a problem for the cyber-physical systems that we're interested in, is that every node is a single point of failure. If any node stops sending messages, all nodes become unable to process messages henceforth, and that's going to create a serious problem because the entire system grinds to a halt. So another solution, which was proposed in the mid-1980s by Jefferson, is called time warp. And there, what happens is that if this web server in Dallas receives a query and timestamps it with R, it simply speculatively executes it and handles it. And then if it later sees a message with an earlier timestamp, it simply rolls back to a previous snapshot of its state and reprocesses the messages in the right order. The problem with this one, of course, is that you can't backtrack side effects. So if your web server has issued a reply, you can't take back that reply. And the second thing is that there's actually quite a lot of overhead associated with doing these snapshots, and there's uncontrollable latency in processing messages, because when you receive a message, if that message happens to be out of order, you may have to backtrack and do quite a bit of processing to catch up to the current state. And so the time that it takes you to process messages becomes actually quite unknowable in such a system, which again is going to be particularly a problem for cyber-physical systems. So a third approach, which is also one that, this is one that started getting into widespread deployment in the 1990s, led by a project at the US Navy where they called this solution a high-level architecture, is where you have a runtime infrastructure that mediates the advancement of logical time in each of the components. So what happens is that when you have when you see a timestamp, when you create a timestamped message with timestamp R, you notify the runtime infrastructure that your earliest timestamped message has timestamp R, and each component does this. And when the runtime infrastructure has heard from all the components, then it can find the smallest of all those timestamps and respond with a time advance grant to every portion of the system, which can then advance its time and process the message with the least timestamp. This, of course, has this essentially the same problem as the Chandy and Misra approach, because it's going to require a lot of null messages from each of the platforms. When they have nothing to say, they're going to have to tell the runtime infrastructure that they have nothing to say, and they have to timestamp those informational messages. And in addition, the RTI, and in fact every component, is again a single point of failure, because if any component stops sending messages, then none of the components are able to advance their notion of logical time. So none of these classical solutions solves the problem. So how does Spanner solve the problem? Well, it's rather simple. So what Spanner does is that when it has a message with timestamp R, all it does is it watches its local clock. And when its local clock exceeds a pre-computed threshold, which is a number, R plus W plus L plus E, then it processes the message. Okay? So how does it do that? Well, the first assumption is that there is a local clock on each platform, and that those clocks are used to derive the timestamps. So when the web server receives a query, it uses its local clock to assign a timestamp to that query. I want to point out right now that we're already in quicksand, okay? Because we now have 3 timelines in this picture. We've got 2 local clocks that don't necessarily agree, and we have a logical timeline, which is the timeline of the timestamps. I have learned from experience that when you try to form English language sentences that talk about more than one timeline at the same time, it's difficult. In fact, impossible. Natural language doesn't have constructs for talking about more than one timeline. And you get sometimes into ridiculous situations where it becomes very, very difficult to express a rather simple concept because very common words like when become overloaded because you have to specify which timeline you're referring to whenever you use a temporal operator like when. So explaining what's going on when you have more than one timeline can really be a challenge, and you have to be very careful with the wording of your sentences and your explanations. So the third assumption here is that we can bound the execution time of this component and that we can bound the network latency. So once we have these assumptions, we know that if there is an event at this web server component with timestamp T, then that event will be known on platform B by time T plus W plus L. But unfortunately, this time is with respect to the clock on A, not the clock on B. But according to the clock at A, at this time, the platform B will know about this message with timestamp T. So now we have to make another assumption, which is a bound on the clock synchronization error. How far off can these 2 clocks be from one another? So if we assume that they can't be off by more than E, then the event will be known on platform B when platform B's clock hits T plus W plus L plus E. This is what leads to this spanner solution, which is that the event with timestamp R is safe to process when the local clock exceeds this threshold, R plus W plus L plus E. So this is, from a pragmatic perspective, a very nice solution for several reasons. One is there's no extra network traffic that's being generated to send around null messages. There's no traffic saying, I have nothing to say, I have nothing to say, I have nothing to say. A second advantage is that we've made a bunch of assumptions, right? But every one of these assumptions is very explicit and quantified. The assumption W about the execution time of this database component, I have to know what that number is to have a solution. And so now my verification problem decouples. I just have to verify that, in fact, that execution time is bounded by W. My network latency assumption is, of course, network latencies, particularly in an internet context, are very hard to bound. But in a distributed real-time system, you really can't do anything without bounds on network latency. You can't make any assumptions at all about any coordinated action if you can't bound network latency. And all too often in embedded systems, you do make assumptions about network latency bounds, but you don't make them explicit. And this formalism forces you to make your assumptions explicit. You have to tell me what is your assumption about your bound on the network latency. And the clock synchronization error, similarly, you have to make that assumption explicit. And again, you can now decouple your verification problem into one where you verify that, in fact, your clock synchronization mechanism will provide this. So for example, if you're using an ARINC bus like is typically used in aircraft, that actually has a clock distribution mechanism as part of the network system itself, and there is a bound on the skew between the clocks at different points in the network, and you can quantify what that bound is, and so you can come up with this number L fairly easily for that kind of a network. So very nice features that this has, making assumptions explicit and not generating any network traffic. There's also no single point of failure. If any one component fails altogether and stops sending messages, every other component can continue operating because all it's doing is processing its messages at a time that is determined by watching its local clock. The latencies in processing messages are well defined also, because now I can start with a requirement that this web server should reply to queries within 30 milliseconds, for example. Maybe that's a requirement that is driven by human timescales. I want a web page to tell me within 30 milliseconds whether a seat is available. That's a requirement. So given that requirement, I can now say, I now have a criterion under which to choose an implementation technology. I need for the sum of these three numbers, W plus L plus E, to be less than 30 milliseconds. That tells me something about what networking technology I can use and cannot use. And it tells me what I should do about clock synchronization. And it tells me what I should do about execution time. So having those requirements that can be derived from the end user specifications on latency is also a very, very valuable property of this mechanism. Moreover, once you know the structure of your application as a whole, the time thresholds that are required for that you have to watch your local clock before you process a message, those can be derived from that structure. So you can, in fact, know these statically once you know the structure of the program. One of the interesting things about this scheme is that when failures lead to violations of the semantics, in other words, out of order processing of messages, they're always detectable. If any component gets a message with a timestamp that's earlier than a message it has already processed, that component now knows that one of the assumptions was violated. So you have a detection mechanism for violations of your assumptions, which means that you can build a fault-tolerant system on top of this that looks for these violations and switches your mode of operation into some safe mode, for example, when such violations are detected. Okay, so this architecture is not at all at odds with designing fault-tolerant systems. In fact, it facilitates designing fault-tolerant systems because it very clearly defines what the correct behavior is, and it provides a mechanism for detecting incorrect behaviors. If you ever see out-of-order messages, you have an incorrect behavior, one of your assumptions was not satisfied. This is often a problem with designing fault-tolerant systems, right? Every system you design is based on some assumptions. Violations of those assumptions are often not detectable. But in this case, they are actually detectable. Okay, so Google was not the first to invent this technique. In fact, usually with good ideas, the people who get credit for inventing an idea are the last people to be first to invent it, because they independently came up with it in 2012, or at least that's when they first published it. And we had published a paper 5 years earlier in 2007 where we used exactly the same technique for cyberphysical systems. And it never occurred to us that this would be useful at the scale of a system like Google Spanner. We were thinking more like factory floor kind of systems, but it's nevertheless, it was a tremendous validation that this technique could actually be used. So the model of computation is deterministic. Okay, I want to emphasize what it means to be deterministic. Deterministic doesn't mean that the behavior of the system in the field will be perfectly predictable. The behavior of the system in the field can always deviate from your design. That's a fact. Okay, Murphy's law can always kick in. What's deterministic is the model. It's the model of the system that is deterministic. So given particular time-stamped inputs, you have a well-defined response to those inputs. And it's a unique response. And it's that uniqueness of the response. There's only one correct response given a set of time-stamped inputs. That's what makes the model of computation deterministic. And having a deterministic model of computation is extremely valuable because it defines very clearly what correct behavior of the system is, which is part of what enables fault detection. So what's the cost of determinism? Well, one of them is that you have to have synchronized clocks. Here's a picture of non-synchronized clocks. This is on the Clark Kerr campus at Berkeley. I think these clocks stopped years ago. But the fact is, synchronized clocks are becoming ubiquitous. In fact, all of the network gear that you can buy these days has hardware support for very fine-grained clock synchronization. For the most part, these synchronized clocks have not yet elevated to the software APIs that we use every day. The fact is that your Wi-Fi chip on your laptop and your Ethernet chip both have clocks that are very tightly synchronized with clocks in the network, but you don't have access to those clocks. You have access to a system clock that is much more coarsely synchronized using a rather old protocol called NTP. And it's not a very high precision clock synchronization protocol. NTP is pretty ubiquitous, and it does have, there are reasonable bounds on the clock synchronization error, but they're on the order of seconds. Whereas the clock synchronization protocols that are getting much more widely deployed are synchronizing clocks down to scales of microseconds, or in some special cases, even nanoseconds. So I predict that before too long, there will be standard POSIX APIs for getting access to very high precision synchronized clocks. And I think the only thing holding it back is that people haven't quite yet realized how valuable it is to have those. Bounds on network latency, of course, are a problem. In fact, most people think of TCP/IP when they think of my requirement that we have bounds on latency. And in fact, TCP/IP is not so widely used in embedded system design precisely because it's designed for a different purpose. The purpose of TCP/IP is to provide reliable in-order delivery, and it's supposed to be reliable even in the face of the network becoming overwhelmed by too much traffic and switches in the network dropping packets. So the TCP/IP protocol includes retransmission protocols and acknowledgements, and bounding the network latency can be quite difficult. In fact, in the Google Spanner case, they do use TCP/IP, but they're connecting the data centers with dedicated trunks, so they have some control over the load on the network that is flowing between the nodes in the database. And as a consequence, if you can control the load on those networks, it's actually not so unreasonable to bound the latency, even in that case. But you do have to you do have to deploy a system like this in a context where you can have reasonably high confidence in your bounds on network latency. There's a very promising new technology that is being in the process of being standardized by the 802.1 subcommittee of the IEEE, which is the subcommittee that's responsible, was formed initially to standardize Ethernet, but it's actually standardized quite a lot of other things since then. But this family of protocols is called TSN, which stands for time-sensitive networking, and it promises to bring the ability to have bounded network latency even to open internet contexts. So once that gets widely deployed, you could even use this technique on an open network, open internet application. But for now, you probably have to have more control over the network in order to be able to bound the network latency. You also need to be able to have bounds on execution times but you only need these in particular places in the system. It's particular points of the particular pieces of code that have to have bounds on the execution time, and you know a priori which are those pieces of code that need to have those bounds. And we have another project that is all about providing very, very tight execution time bounds, but that would be a subject for an entirely different talk. So let's go back to the requirements that we wanted to formally verify. Which of these requirements can we in fact verify with the Ptides spanner approach? Well, the first one, we can actually verify a stronger requirement than I initially stated, which is that if the door receives open, it will open the door in bounded time, even if all other components fail. So that's a stronger requirement than the eventually requirement. The second requirement, I have to weaken. If any component sends disarm message before, now before means its timestamp is earlier. Any other component sends open, and the message is received in bounded time. I have to add that additional clause. Then the door will be disarmed before it is open. So the first requirement is stronger, the second requirement is weaker, but these two requirements would be guaranteed by the model of computation. And so if the model of computation is reliably implemented, then you have an implementation that will satisfy these requirements, and you don't even have to do very much to formally verify your program. Now, how are we realizing this? So far, I haven't talked at all about Lingua Franca. So let me talk about Lingua Franca. Lingua Franca is a concrete realization of this discrete event model of computation. You can download the code from this GitHub repo, go to the wiki for documentation on this. It is a polyglot language. It is not a programming language. It's a framework within which you build programs in your favorite programming languages. We have currently an implementation that supports C, an implementation supporting C++, and an implementation supporting TypeScript. And you might think that's a rather odd choice of languages, but it's a rather deliberate odd choice. We chose to focus on C because we want to identify the lowest overhead that is possible in an implementation of this language. And C is the sparest language out there for doing that. And we chose TypeScript because it's at the opposite end of the spectrum on languages. It's a tremendously heavyweight. It's a dialect of JavaScript. It's a type-safe version of JavaScript that was developed by Facebook. And it's a rather heavyweight language with garbage collection and a lot of dynamics to it. And we wanted to make sure that the language could cover that entire range, that the Lingua Franca framework could cover that entire range. So I'm going to focus on the C target. So here's a hello world program in Lingua Franca. It specifies that the target language is C. And then it defines reactors, one of which is a main reactor. And there's this funny syntax with these curly brace equals that surrounds code that's in the target language. So this printf is ordinary C code. So everything outside of these funny curly brace equals is Lingua Franca, and everything inside is C. Events of various kinds trigger reactions, and there's a built-in startup event that will be triggered when the program starts up. And when you run a distributed program, there's a coordinator that ensures that they all start simultaneously, as much as you can make them start simultaneously. They start with the same logical timestamp and the same, as close as you can get to the same physical time. In a departure from actor languages, we use hierarchy and ports. And the reason for this is that it gives us a tremendous amount of information about dependencies between reactors that is absent in actor languages. So you can have a reactor A that has an output named Y. You can have a reactor B that has an input named X, and you instantiate and connect them using a syntax like this. So an application sketch might look something like this, where you have, for example, our aircraft door might be one of these actuators that receives messages to open or disarm. And you have aggregators that can receive messages from multiple sources, and you have sensors that can timestamp messages using the local physical clock. A reactor that simply passes through messages The way it would be specified is you give it an input, you give it an output, you define its state variables with initial values. You say in reaction to an input, it produces an output. This is a conservative description of the dependencies, because what it really says is that the target language code may produce the output Y, not that it does produce the output Y. Okay, we don't analyze the target language code. We don't know what it's going to do. It might do nothing at all. So we can't ensure that the output is produced, but we can prevent it from the output from being produced if you didn't declare that it might be produced. The inputs are time-stamped. Outputs are logically instantaneous with the inputs. So it shares this feature with synchronous languages. In fact, this is a feature derived from synchronous languages, and it's a very powerful feature. It turns out to be a key to the extreme efficiency of the implementation of Lingua Franca. I'll talk a little bit about the numbers in a minute, but the fact that the outputs are logically simultaneous with the inputs has led to an implementation that is extremely efficient. The reaction signature tells you about the dependencies so that you can do the kind of analysis that we need to do in Ptides, where we can determine how long you need to wait in order to process events. The overall model of computation, as I said before, is deterministic. You can have a component here, for example, the meaning of this is that this component will react to messages at input port in1 or in2. It reacts at a particular logical time. At that logical time, the input may be present or absent. If the two messages have the same timestamp, then they will both be present in the same reaction. Okay, and that's guaranteed by the framework. And this is what the syntax looks like in C if you want to do something specific with those inputs. So whether the two triggers are present simultaneously depends only on their timestamps and not on when they are received or where in the network they're sent from. Time is a first-class citizen in Lingua Franca, so we have a very nice syntax for specifying and presenting time. So for example, I can specify a timer that starts 1 millisecond after the overall program starts and then ticks every 100 microseconds. And in reaction to that, I could poll a sensor, for example. In the C target, timestamps are 64-bit integers that represent the number of nanoseconds since January 1st, 1970, if the platform has a clock, or the number of nanoseconds since starting the program if there's no clock on your platform. And we have run Lingua Franca programs on platforms with no clocks. In fact, we've run it on platforms with no operating system even. You can have event-triggered behavior. The way that works is during your startup reaction, you can set up an interrupt service routine, and the interrupt service routine will call a built-in function called schedule, which will trigger what we call a physical action. So it's the physical action that is actually responsible for assigning a timestamp. And then you can have a reaction to the physical action, which will do some processing and produce an output, maybe. So you can specify deadlines, and the way you do that, the syntax is that you specify that a reaction should occur within a deadline of 10 milliseconds. And again, explaining what this means is treacherous because it involves more than one timeline. A deadline violation occurs if this reaction is triggered in physical time more than 10 milliseconds later than its timestamp. It's very easy to state that, to make that sentence incorrect by not being very careful about the wording of the temporal operators, but that's what the deadline means. So deadline is violated if the input triggers more than 10 milliseconds in physical time after the timestamp of the input. So the status of the project is still early. I'll give a quick demo so you'll get a sense of what this is about, but you can also download it from the code. I'd like to just talk a minute about the performance. I'm actually astonished by the performance. I have a lot of experience building discrete event systems, and I've never seen a discrete event system that comes within orders of magnitude of this level of performance. What we're seeing on my laptop is up to 28 million reactions per second per core. And we can automatically exploit multiple cores. We have a multi-threaded implementation that will use all 8 cores of my laptop if there's enough parallelism in the application. So that's roughly 36 nanoseconds of overhead per reaction invocation on my laptop. The code is extremely small. The Lingua Franca compiler takes this input in the C target and produces a standalone C program that is tens of kilobytes in size. So it's very suitable for use in deeply embedded applications. So I already talked about clock synchronization. What I'd like to do is talk about distributed execution, and let me do this briefly in the context of a demo. So I have only 5 minutes left, so this is going to be a quick demo, but it'll give you a sense of what the framework is about. So Lingua Franca, you can, when you download it, you get an old-fashioned, it's actually not very old-fashioned, it actually uses some pretty sophisticated technology, but you can use it in an old-fashioned way as just a command line compiler. So you have a .lf file. Here's a Lingua Franca .lf file, and you can just run a command line compiler and it'll produce a standalone C program that you can then execute. But we also have an Eclipse-based IDE that is much nicer to use and has a visualization of the program. So this is a Hello World distributed program. So the top level reactor, the main reactor, is this one. It instantiates a message generator and a print message. So the message generator is a reactor that dynamically creates a string to send a message to a print reactor, okay? But the trick is that I would like to now deploy these on a distributed system. So I do that in the target specification up here by specifying that there are 2 federates in a federation. The sender federate has the instance of the message generator, and the receiver federate has an instance of the print message reactor. And because of specifying this, when the Lingua Franca compiler runs, instead of generating 1 standalone C program, it's actually going to generate 3 programs. It generates a coordinator, which we call the runtime infrastructure, and then it generates programs for each of the federates, okay? So the message generator will be mapped onto one processor, and the printer will be mapped onto another one, potentially. And then there's a communication between them, which by default preserves timestamps. So I can send this, make sure the syntax is correct. I can send it in such a way that it will guarantee to preserve timestamps. So every time I save my changes in this IDE, a C program gets generated. In fact, you can look I'm in the directory where that Lingua Franca file is. So distributed.lf is a Lingua Franca file. And I can look at the source gen directory and see programs that were generated at 12:29 p.m. on April 16th, which is right now, okay? And there were these 3 C programs that were produced by the compiler. They were also compiled and put into the bin directory. So I can now start these 3 programs, and I can start them in any order. So let me start the RTI here. So the runtime infrastructure is just now listening for connections from the federates. I'll go to a different window, which is in the same directory, and start the sender, okay? And it reports that it has successfully connected to the RTI, but nothing is happening yet because the RTI coordinates the start of this federation, and it can't start until all the federates have joined. And so I will start the receiver. Oops, oh shoot, it looks like I had 2 RTIs running. There's a
Or I think you might have Control-C'd out of the RTI that you had started.
I probably did. Okay, so let me start it over. So here I've started the RTI again. By the way, one of the things on our to-do list is to automatically build in authentication and encryption. When you generate these three programs together, you could generate these programs in such a way that these three programs can only talk to each other and that they can talk over encrypted sockets, right? So no other separately generated program will be able to connect to this RTI. But we haven't done that yet. So let me start the sender again and then start. Yeah, I think what I did was I was confused about which window I was in. Okay, so this, once all three pieces have started, then you can see that the receiver is receiving messages, and it tells me that the timestamps, that these are actually relative to the start time. The start time, here's the timestamp for the start time. This is how many nanoseconds have elapsed since January 1st of 1970. And the timestamps are 1 second later than that, 2 seconds later than that, 3 seconds later than that, and so forth. The sender sent at those same timestamps, okay, and it sent these messages. And the RTI shut everything down when all of the federates had departed. Now, we also have a mechanism where you can use a more decoupled execution, which we indicate with this sort of squiggly arrow. And now the timestamps will not be preserved. So in fact, what will happen at the receiver is that a new timestamp will be assigned to each incoming message based on the local physical clock. So this actually gives me a way to measure the communication time between these federates. And if you look at these numbers carefully, you can see that the latency for communication between Unix processes on my Mac is on the order of like 3 to 5 milliseconds. That's just a fact about socket communication between processes on a Mac. Okay, so you have these two different mechanisms: the deterministic mechanism, which preserves timestamps across the execution, but is based on certain assumptions like synchronized clocks and bounded network latency. And then you have that second option, which for some applications is perfectly adequate, which is a non-deterministic mechanism that reassigns timestamps at the receiving end and doesn't require any of these assumptions about bounded synchronization, bounded clock synchronization error, and so forth. Okay, so let me close quickly with just a couple of observations. Here's a few of the questions that can be addressed by Lingua Franca. One is, how do you get repeatable and testable behavior even when communication is across networks? Second question is, how do you specify, ensure, and enforce deadlines? Third question, which I haven't talked about much today, but with a little imagination, you can see how this could be done. What combinations of periodic, sporadic behaviors are feasible? Under what conditions can you meet your deadlines? Okay. How do execution times affect that feasibility? And then finally, since we have a deterministic overall model of computation, if you assume a correct execution, does your program meet its specifications? So in conclusion, these programs are testable because given a set of timestamped inputs, there's exactly one behavior defined by the program. It's a set of timestamped outputs. And so you can use this very simple regression test notion of testing, which is you have test vectors and you have correct responses, and you can use that to test your program and to test your implementation of the program. The Lingua Franca programs are deterministic under clearly stated assumptions. Violations of the assumptions are detectable at runtime, and actors and publish and subscribe buses and service-oriented architectures have none of these properties. So if you're interested in this, we're certainly very open to more collaborators on this. There's a lot of work to be done. If you go to the wiki, in fact, there is a to-do list, some of which are really PhD thesis topics rather than software projects. Some of them are just software projects, but there's a mix of both on the wiki. Thanks very much.
Thank you, Edward. And are there any final comments, discussions? So I have one question myself. Is when you know, one of the problems is that assume that the timestamp are coming very close to each other. Then when you have lots of events that you need to process, is that going to affect the speed of the program? I assume so, but have you done some experiment?
Yeah, of course. There's, any program, any software system can get overwhelmed if you give it too much stimulus. One of the interesting things about the Lingua Franca design is that we actually give a way of regulating the stimulus to the program. So when events occur asynchronously, well, sorry, first of all, the timer mechanism gives a way to specify events that are regularly spaced in logical time. And we align that logical time as closely as we can to physical time, so that actually gives a mechanism for regulating the load as well. The problem occurs, of course, with asynchronously generated events that are generated by the environment. So for example, messages coming in over a network or anything like that. So the mechanism that we have provided for creating events and timestamping them has a property that you can add, which is a minimum inter-arrival time for the messages. We call it the MIT. I'm an MIT alum, so I can use that term. But the minimum inter-arrival time.
Everybody has a little blemish in his past, right?
Yeah. So if you specify a minimum inter-arrival time, then the software implementation will in fact enforce that you do not generate events that are spaced by less than that minimum inter-arrival time. So that gives a way to sort of isolate your system from a misbehaving environment. If the misbehaving environment is trying to generate events that are going to overwhelm your system, we have a mechanism where you can gateway the entry of those events automatically. Once you know that minimum inter-arrival time, you can actually use something like a network calculus to look at how the load propagates through your system in a worst case, because we have the dependence analysis, we have the dependency information in the program that tells you which events can possibly cause events later in the chain. Okay. So a network calculus is a very nice way to actually construct a formal description of how a load will propagate through your program. So we have mechanisms that enable both this gateway mechanism to protect yourself from a misbehaving environment, and also mechanisms for doing analysis of the load throughout the program. Now, I say we have these on our to-do list. I see at least one, maybe a dozen PhD theses could be written about this analysis.
Yeah, I can see that too. Now, by the way, there is in the old times, in the first generation logic simulators, we had a concept, especially in mixed mode, when you had mixed, continuous, and discrete time, we had what was called minimum resolvable time, which looks like the same. So the minimum resolvable time is essentially the base clock, if you like. And so everything could be considered synchronous on the minimum resolvable time.
Yeah, I'm not sure that I would use that term for this, because I would use the term minimum resolvable time for the granularity of the clock, which in our implementation in Lingua Franca is 1 nanosecond. And so that's just a fixed number because our representation of time is an integer number of nanoseconds. I would call that the minimum resolvable time.
You can express the MTI, MIT, whatever, MIT in MRT, right?
Yeah, the MIT can be any number of nanoseconds, but it has to be an integer number of nanoseconds.
Yeah, so it's a multiple of MRT.
Yeah, right.
In that sense, yeah, okay. So I'll let the class be dismissed, and we may have another Zwine in which we discuss all of this.